Now we're going to show Newton's derivation of Kepler's third law. So all this comes from circular motion. Last year, when you studied circular motion, you knew that there always had to be a force directed inward to cause the object to keep moving in a circle. So what provides that centripetal force for orbital motion? Well, it is the force due to gravity. So if we do a quick little force balance for a planet, the only force acting on it, all right, so we're going to sum up the forces, the mass times acceleration, this is centripetal acceleration, right? Since the only force acting on it is force due to gravity, Fg is equal to m times centripetal acceleration. It's the mass of the planet times the centripetal acceleration. So if we're going to substitute in Newton's law of reduced gravitation for F sub g, it's going to be big G times big M times little m divided by r squared, the separation of the two objects, is equal to m times the centripetal acceleration. The mass of the object that is doing the orbiting will cancel out the little m. There we go. All right. So what we're left with here is big G times big M over r squared is equal to centripetal acceleration. We know that the centripetal acceleration is also the same as v squared over r, so I'm going to rewrite that here. All right. Big M over r squared is equal to v squared over r. Okay. Do a little bit of algebra. All right. Get rid of this r on this side. Multiply both sides by r. All right. And cancel out here. Here gets rid of one of these r's in the denominator. So we're just left with r there. So we have big G times big M, excuse me, all over little r is equal to v squared. We also know, all right, so up here we said the centripetal acceleration is equal to v squared over r. I'll write that here as the steps that you see it. All right, we also are going to substitute here for v. We know that v is equal to 2 times pi times r all over the period big T. All right. So we'll substitute that in, and we have big G times big M over r is equal to square of the quantity 2 pi r divided by big T. All right. So in this derivation, we have this. Combine these r squared terms, all right? And when we do that, the whole thing, I'm going to combine the constants on one side and the variables on the other side. So we have big G times m all over 4 times pi squared is equal to, oops, smartboard's died here. R cubed over t squared. And I'm just going to flip all that around because the way we're used to seeing it actually is just t squared all over r cubed is equal to 4 times pi squared over g times m. So hopefully here you're seeing where we got that relationship from the very first slide. We got t squared is equal to some constant 4 times pi squared all over g times m. And that's all times r cubed. Okay. If you take the square root of both sides, it becomes r to the 3/2 power. Like I showed you on the first slide. So let's use this derivation, all right, to weigh the sun. Well, if we know that the period of the Earth's rotation around the sun is equal to 31,536,000 seconds, all right, and the radius of the Earth's rotation around the sun is 1.5 times 10 to the 11 meters. Substitute those into what we just got before. I'm going to rearrange that equation. You can do it on your own if you want to, but the big M, which is the mass of the sun causing the object to do its orbit, is equal to 4 times pi squared times r cubed divided by g times t squared. Substitute in all of those values, and you end up with m is equal to 2.0 times 10 to the 30th kilograms. All right, the accepted value is 1.99 times 10 to the 30th kilograms, so it's pretty close. All right. The next one, using this derivation of Kepler's third law to weigh the Earth. What I did is I used the moon for this. The orbital period of the moon, right, is equal to 27.32 days, and that's times 86,400 seconds per day, and that leaves us with 2.36 million seconds. All right. When you substitute all those values, you end up with 6.03 times 10 to the 24th kilograms. Oh, and for the orbital radius, I think I used 3.84 times 10 to the 8th meters. The accepted value is 5.98 times 10 to the 24th kilograms, so that's reasonably close for what we're doing here. All right, that's it.